Okay, first you run the cell, the first cell, and see os.list directory path 1. And if I type files, you can see it will display all the image names. See, just for the demonstration purpose, I have uploaded only limited files. If I check the length of the files, only 90 images only I have uploaded. But if you wanted to seriously build for your own project or a research work or any application when you build, as much as possible, you have to use many samples as much as possible. Because when I execute this in lively, it will take too much of time when I have thousands of images. That's why I restrict to 90 images on the affected case. And any one image, if you wanted to visualize, I can say plt.imread path 1. Currently, this path 1 is affected folder. In files, you have seen all the file names, right? Randomly, I take one of the index 14 index file, and I'm checking the shape. Look at the shape, it is 130 by 130. Another image you randomly check, the shapes are, this is 130, 133. This is 121, 121. Another image you check, it is 103, 124. So all the images are not in uniform size, isn't it? That is the reason we are going to standardize all the images to uniform size, 100 by 100 size. So if you can visualize the image, any one image, maybe it is at index number 11. This is a malarial cell. At index number 14, if you wanted to check. Okay, this is a different. So any image you can randomly check and standardize. We are going to standardize all the image to uniform size, 100 by 100. I'm not going to run this for loop because if I run this for loop, it will take at least 12 minutes to convert all the 90 images. It is going to process and it is going to save it in the path 3. It is going to save because in my processed folder already all the processed images are already being saved in path 3 as well as path 4. So I skip running this cell, but you have to run this cell. Okay, you have to run this cell. Then only you can fill all the images in the path 3. Path 3 affected processed. Otherwise, your affected process will be empty. Okay. So I skip running this cell. Now my OS list directory is referring to path 3. Sorry, path 2. os.list directory to path 2. Now files. Now if I check the length of files, who is in the path 2? Second class, right? Second class, I have got 85 files. In the class 1, I have got 90 images. In class 2, I have got 85 images. So when I check length of the files, you can see 85 images. This is uninfected. So what I do here for file in files, this time it is going to accessing these 85 files. And then you have to run this loop. So, and you are saving the result in path 4. I'm saving the result in path 4. That means you are filling uninfected processed. You are completely filling. So these two for loops, as soon as I ran, okay, the two folders are available with me. Now in the next step, what I'm going to do, okay, so I'm going to read all the images and I'm going to put it in a form of an array format. What is the size of each image? The size of each image is 100 cross 100, 3-channel color image, isn't it? So 100 cross 100 is 10,000, 10,000 into 3, which is 30,000. 30,000. How many images totally we have in path 3 folder? In path 3 folder, affected process, affected 90 images, isn't it? So each and every image I'm going to take and I'm going to convert this as a flatten. I'm going to flatten it. 100 cross 100 into 3, 30,000 pixel. I'm going to flatten it. Why I'm flattening it? There is a reason, because we are going to generate the labels. After generating the labels, once again, we are going to bring it back to original dimension, 100 cross 100 by 3. So we can do the reverse process. So this two-dimensional array format, it is creating np.array of while reading. So I'm reading all the images from the affected processed folder. After reading this, you can see the dat.shape 90 cross 30,000. Okay, I have to run this because you are going to read this time. You are going to read from affected processed, right? So my file identifier should direct to the path 3. So what I need to do, I need to run this files 3 os.list directory path 3. I have to run this now. Files 3 is the identifier referring to the processed folder because I have used the file 3 as a reference here for file in files. So it is loading all the processed folder, all the images of uniform size 100 cross 100 of color channel, and it is going to put in a two-dimensional array format so that we'll get 90 cross 30,000. In the meantime, I have to do the same process for the fourth path that I've saved in files 4. Files 4 reference is os.list directory path 4. I am keeping files 4 as a reference for the processed folder second class. Let us cross check that length is 85, right? So now we have created one two-dimensional array 90 by 30,000. Another two-dimensional array I'm creating from those 85 files. I'm loading this. We can verify dat to shape. Dat to shape, I should get 85 by 30,000. See, even the loading itself, how much time it takes. At least it takes around 20 seconds, right? Roughly 20 seconds. That for loop, if you execute, it will take around 10 to 12 minutes. So randomly one image I accessing just for the display purpose. Similarly here also, because in dat, no, we have kept all the images in a form of a flattened version. It is a flattened version, right? If at all, if you wanted to visualize one image, you access one row, you can reshape 100 by 100 by 3. You can see it in a 2D format. That is what I'm doing here. Randomly, I'm just picking one of the 19th index. 19th index. I'm accessing the 19th index. All the columns I'm accessing with the reshape 100 100 3. I display that image. You can visualize in a 2D format. That means both the process are reversible. Okay, you are flattening it. The flattened portion can be again you can bring it back to the 2D format like this. Any other image also you can verify. Maybe like the 25th index I wanted to check. Okay, it's a different image. These are all the affected cases. This is the unaffected cases. Also, you can randomly check 20th image having a slightly different pattern. Okay. So what we have created dat and dat2. So what is the shape of dat? The shape of dat is 90, 30,000. We have a shape of dat2 which is 85, 30,000. Now the next step, we are going to concatenate both vertically like this, so that we are going to get 175 cross 30,000, isn't it? After concatenation. So the first 90 images belong to class 1. From 91th image till the last 175 belongs to label 2. But in Python index, starting from 0 to 89th index, and again 90th index to 174th index in the Python index. So next step is concatenation. So we do the concatenation here. After concatenation, our complete data is 175 by 30,000. Okay. So that is being saved in that complete all the records, 175 record, we converted to 30,000, one dimensional. Now this is a very crucial part, labeling. I know that which order you have concatenate, you know it, right? The first 90 images belong to class 1, next 85 images belong to class 2. Till the time labeling, you are not supposed to shuffle all these things. What I create label equivalent to np.zeros, number of samples. What is the number of samples? The total number of samples, 175. That means we are creating an array, okay, zero array. 175 zeros we create. 175 zeros we create. We know that out of the 175 initialized zero, we know that first 90 images belong to class 1, right? I say label colon 90 till 90th index. 90 means, if you say colon 90 means in Python, it will take from 0 to 89th index. It is going to fix label 1. And when you say 90 colon, starting from 90 till 174, it is going to keep the label 0. Suppose if you have 3 classes, imagine the same thing you do it. Concatenate all 3 together like this. Class 1, class 2, class 3. According to the size, colon 300, you can give label 1. And 300 colon till the end, you can give the label 2. This is the way you can assign the label. First, you assign the integer label. Later on, you can convert that to one-hot encoding. That's not an issue. Okay. First, when you generate the label, first you have to generate the integer labels. So in this portion, I'm creating the labels. After creating the labels, num sample has not been updated. You can see the first 90 belongs to label 1. From 91th index till the last record belongs to second class. So whichever the way you wanted to label, it's your choice. I wanted to label all the affected cases, malaria cases as a label 1, and non-malarial cases, I kept it as label 0. Okay. So after labeling, what we are going to do, now you can shuffle the records. Till the time labeling, you have to maintain each class in a respective folder. Now what I do, I shuffle the complete data along with the label. That is very important. Your data will be shuffled along with the label. So all the shuffled records will be in the updated variable called data and along with the label. So your data and label will be intact. Okay, let me run this in separate cell to give an idea. Let me run this in a separate cell. Okay, suppose I run this. After running this, I check data dot shape Still it is 175 by 30,000, but it is being shuffled, not in the order. First 90 malaria, the next 85 is non-malaria. It's not like that order. Suppose one of the image, if I wanted to know what is the first record in this after shuffling, I wanted to know means you can check this label LABEL. You can see ones and zeros are shuffled. First two records are malaria, third record is healthy. Okay, next to four records are malaria, next to two records are healthy. Completely shuffled. So since you have the labeled intact, which locations, which record is being pushed out, always we can keep track of. I know first two records are malaria and the third record is healthy. How do I know? Because with the reference of the label. Same manner, your data also being shuffled. Now you can use this data along with the label. I'm using the data along with the label to split my record into training set and the validation record. Here I split the record. Okay, we do the train test split here. After splitting the record, remember you bring it back to the TensorFlow Keras format, because time is, as of now it is a one-dimensional flattened 30,000, right? We are bringing it back to the training shape. Training after splitting, see here 30% I am reserving for the testing, 70% we are using for the training. So 70% of 175 record is roughly 122. Okay, it will round off, and remaining 30% of the record will be taken for the validation. So we are representing X train and X test according to number of records, 100 by 100, 3 channel, this time color channel, converting to float 32 and scaling the data to 0 to 1. So I perform this step. You can see this is only the validation record. So X train, I told you this will be 122 point, you got fraction, right? It will round off. If it is above 0.5 means it will round off to the next value. So it's below 0.5. It is rounded off to 122 records. So 122 records for the training and 53 record for the validation. This is X train. Okay, but X underscore train, we have reshaped according to the TensorFlow, right? When I check the shape of X underscore train, you can see the same 122 records. It is being reshaped to the actual color image format, 100, 100, 3 channel. So similarly, your test image, 53, 100, 100, 3 channel. 53, 100, 100, 3 channel. Okay. Now your data preparation part is over. Data preparation part is over. Now, as of now, we have the labels in the integer format. I'm converting the label to one-hot encoding. Because we have two classes, so output side we have only two nodes. Say for example, Y train. First record, if I wanted to see. Okay, 0, 1. Your second node is 1. Y train. Next record. Next record also belongs to the same class. Third record, let me check. It belongs to a different class. Okay. So 100% probability, 0% probability. Okay, when the first node take 100% probability and second node take a 0% probability, which is being converted to one-hot encoding. In the previous example, we have got 10 neurons, right? 10 neurons, but here 2 neurons because we have only 2 classes. And this is where the model building. So you start with model sequential. I'm using a convolution layer with 16 filters, each filter size 3 by 3. What is the input shape? 100, 100, 3. Previous example, 100, 100, 1 we gave. And this is optional. The previous exercise, I didn't do the zero padding. Suppose if you wanted to maintain the input shape, we have given 28, 28, 1 with the 5 cross 5 filter. What is the output we got? 28 minus 5 plus 1. We got 24 cross 24. Suppose if you wanted to maintain same 28 by 28 in the output, in our case, it's 100 cross 100, 3 channel. Okay. And the filter size we are using 3 by 3. What is the output size we get? 100 minus 3 plus 1. We get 98 cross 98. Instead of 98 by 98, if you wanted to get 100 cross 100 output, what should I do? I should say padding same. When I use the argument padding same, automatically your input image will be 0 padded, and it will produce the convolved result also same as the original size of the image. You don't see a very big difference with padding, without padding. It's not a very big deal, but however, just be aware of it. Remember, always in the convolution layer, I should use ReLU activation function. We are using a ReLU activation, followed by max pole 2 by 2. Then I flatten it. So that means only one set of convolution max pole layer I'm using, but with the 16 filters. Okay, with the 16 filters, followed by your fully connected layer. In fully connected layer, I have used 2 hidden layers. This is hidden layer 1 with 256 neuron, hidden layer 2 with 100 neurons, both with ReLU activation function. I told you here also you have options, right? But in the output side, you have to strictly follow this. For binary, you should follow sigmoid. For multi-class, in the previous exercise, we used softmax. Now I'm using sigmoid here. The previous exercise, what we have used here, categorical cross entropy, right? Because of multi-class. But here I'm using binary cross entropy. Here we used softmax, but here I'm using sigmoid because of binary class. Optimizer, here you have 2 choices. You can try with SGD, stochastic gradient descent. Stochastic gradient descent work on fixed learning rate, and ADAM works on adaptive learning rate. Because as the iteration is converging, in one of the yesterday numerical example we have seen, initially your gradient value was 73. After one iteration, the gradient score has reduced it. As the gradient is reducing, naturally your learning rate also proportionately got reduced. That is the adaptive learning rate. And moreover, there is an additional concept called adaptive moment whenever I use ADAM, okay, to escape the local minima trap. So what it is going to do is, adaptive moment, it is going to keep track of how the error is being reduced. It is just memorizing the topography of the gradient reduction, the gradient descent process. Say for example, the gradient keep on reducing it. There is one locally, there is an increase happens, and again started decreasing it. Okay, and this is where the global minima happens. So your adaptive moment, ADAM optimizer, additionally it keeps tracks of what was the last previous landscape, my reduction landscape, in terms of it calculates the differences between the last consecutive few iterations. It will keep track of this. It is calculating the variance score, variance. So what is the variance of my gradient descent profile? Is it a smooth profile or it is a coarse profile? This variance score will give it as a smooth or coarse. If the variance is very high, means it's a highly coarse profile. If the variance is smooth, means it is a smooth profile. So suddenly, if there is a local change that happens, there is a increase in the error gradient. So when the increase happens, okay, so it is keep on tracking the variance calculation across the gradient descent. So when it is calculating the variance calculations at this portion, okay, the variance value will be higher. That means the algorithm will understand suddenly there is one small change in the terrain that is happening. Okay, Whether it is going to have a similar pattern compared to the earlier topography or not, it is cross-check, it will cross-check. Till this point, it's a smooth glide, and suddenly there is one local change phenomena that happened. It is same as the previous phenomena or not, it is checked. It will check it. So this variance is slightly higher than the earlier variance. What it is going to do it is going to give some immediate a thrust factor. We call this a thrust factor or momentum factor. This momentum factor means it's a local boost by slightly increase the learning rate, okay, to escape this region. Locally, it is for that particular iteration, it is going to give a slightly higher learning rate to escape this course portion and to try to see another region and try to see at least 2-3 iterations what kind of variation is there. It will see that, okay, when compared to the previous stage variance, okay, this is a smooth variations, the variance is very less. Here also variance is very less, but in this zone there is a slight increase in this variation that happened. So for the it will maintain a fixed bandwidth. This fixed bandwidth again we can control using the momentum curve. How many last previous step we should consider? That can be play around manually. We can manually change this momentum factor, but it is always advisable to go with the default momentum factor. That is more than enough. So what the algorithm will understand that, okay, whatever this slight increase in the variation that happened, it is just a local phenomena because my current topography still it is in the lower direction compared to this magnitude. This is still at the lower side. Say for example, this is something like 0.426 individual error, but this is around 0.368. It is a reduction that happens. Not only the reduction in the error, but also the topography is very smooth here, like this topography. But this topography is, there is a slightly coarse topography. Let us escape that slight topography. Let us not get trapped with this local minima. That is what your Adam optimizer is going to do. Additionally, along with this, keep track of the individual every stage error gradient. It is keep track of the variance score of the last few steps, iterations, whatever the error we have got. It is keep track of the variance score also. Accordingly, whenever the coarse gradient comes, it try to give a local push. Suppose the local push, it is not coming to the reduction zone. Rather, say for example, this is the final minima, right? This is the final minima. The same phenomena happened here also, right? The same phenomena happened here. See, because it reaches the saturation zone and again started increasing. So the algorithm will see, okay, there is a gradient increase that happened. There is a variance score when it is calculating. There is a again increase. So from the smooth region, again, there is a changeover to some coarse variation that happened. But this time, when compared to the individual error score, like by this time, it has reached somewhere around 0.1365 or something like this. Compared to this score, this is on the increasing trend. Okay, say for example, 1456. Even though it tried to escape the zone, identify this is a coarse zone, try to give a momentum factor to escape the zone, it will be escaping only to this zone. Maybe this zone is a smooth zone, but on the rising trend, it will see that score. Okay, now no more I need to escape this. Whatever the region we have got is a true saturation region. Okay, there is no point in escaping this zone. So escaping this zone is different from escaping this zone, because when I escape this, once again, I will be falling on the descending direction only, not on the ascending direction. But when I try to escape the zone, I'm getting trapped in the ascending direction. So this is the way your adaptive moment will keep track of the variance score, understand the landscape. Accordingly, it will have a convergence. So the advantage of using Adam is we can prevent the local minima trap. But however, always you can try both method. Optimizer with SGD is having a better convergence, or Adam is giving the better convergence. So to have a comparative difference, I run this with SGD regressor, SGD optimizer, and then you can change the optimizer to Adam also, you can try. So when you run this architecture and see the performance of this architecture. So this architecture is being defined, okay, and I'm running this with 100 epochs. So now the iteration started. It will take some time. So in the meantime, when it runs, I will show you the score for this. What is the score we got for this design? Of course, it's a very simple design. Because I have used only 2 hidden layer in the fully connected, and also I have used only one set of convolution layer with 16 filters. For that design, totally we have got 22 non-malarial case, and we have got 31 malarial case. Okay, when we presented 31 malarial case, our model correctly predicting 27 malarial case correctly as a malarial, and 4 cases it misclassifies as a healthy. Okay. Similarly, out of 24 non-malarial case, 14 cases correctly predicts, and 8 cases it misclassifies. So what is the sensitivity of the model? If I wanted to calculate sensitivity, true positive rate, right? 27 out of 31, which is called the sensitivity of the model. So 27 out of 31, if you work out the calculation, 27 divided by 31, 87%. And specificity, at what rate your negative class is being correctly recognized as a negative, right? Specificity, which is 14 out of 22. So 14 out of 22, we got 63%. Sensitivity is 87, but specificity is only 63%. How do I calculate precision and recall for this? Say, for example, recall for this. What is a recall? Recall is same as your sensitivity, right? So your 14 out of 22, that is what we got, 64. It is strictly, it is 63.63, it's rounding off to 64. That's why you got 64 there. Similarly, what is the recall score of 1 is same as your sensitivity, which is 87, isn't it? How do you calculate precision for each class? Say I wanted to calculate what is the precision for the malarial class. Our model predicts not only this 27 as a malaria, this 8 also our model predicts as a malaria. So totally this 27 plus 8, 35 cases, out of which only 27 cases are truly malaria. So the 27 by 35, if you calculate, you get 77%. Similarly, our model predicts non-malarial case, not only this 14, this 4 also. So 22, out of which 14 cases are really non-malarial case. So the precision for non-malarial case is 78. So I take average of these two in the form of F1 score, average of these two in the form of F1 score. So the overall average of these two is 77%. The reason, okay, it's definitely it's not a above average performance, but still there is a lot of scope to improve it. Okay, what are the scope to improvise this? Feature wise, it's not a complex feature. Okay, feature wise, it's not a complex feature. There is no point in increasing the convolution layer. No point in increasing the filters in the convolution layer. The only area you can play around is in the fully connected layer, try to introduce one more hidden layer. I have commented in this architecture. You can uncomment it, rerun it. Okay, with the 3 hidden layer and try to see the performance. Your performance will be improved. Number 2, second way to improvise the performance is you have to expose more records to the model, because your deep learning model is the data hungry models. It is, we have given only very limited set of okay, to generalize the patterns, it requires more records. Like MNIST dataset, we have trained 60,000 records. Okay, not at least 60,000, at least a few hundreds of records we may require. The source page is available in Google. You search for the malarial dataset, you will get the source page. If you go to the source page, you can have around 3,000 plus records are available in each class. 3,000 plus records are there. No need to download the entire 3,000. At least instead of 90 records, at least you can create something like 400 to 500 records, malarial case. And healthy case also, you can create some around, instead of 85 records, maybe you can have some 300 to 400. At least close to 500 records if you upscale the number of records. And also the fully connected architecture, you include one extra hidden layer, And this all, and moreover, I have ran this with SGD, right? The same architecture you can rerun with Adam optimizer. You can see the performance difference with Adam. So these are all the way you can modify the performance. You can see all the 100 epochs as done. Because this time I have enabled the runtime. Okay. If you go to the change runtime type, you can see the hardware accelerator I have given GPU. Okay, yesterday I didn't enable for the yesterday exercise, that was GPU was not enabled. It was running in the CPU. That is why it was taking so much time. 50 epoch, it took so much time. And moreover, it has 60,000 training record, but here this is very less number of training record. So the iteration came very quickly. So there are two reasons. Number one, images are very less number of training images. Number two, we ran it in the GPU, not in the CPU. So we have got a quick results. You can see the validation performance and for the training accuracy and the validation accuracy. Training accuracy is 100%, but the validation accuracy is 78%. That means your model overfits, isn't it? There is a huge difference between training accuracy and the validation accuracy. So the overfit nature is because of too many redundant features or too many neurons in the layer. There are two possibilities are there. Okay, try to reduce the filter and see the performance. Okay, if you try to reduce the filter instead of 16 filter is not necessary for this simple features. You try to reduce the filters, your model will gain some regularization and it will try to maintain the differences. If you reduce the number of filters, that is one way to achieve regularization, stability. Another way is reduce the neurons in the fully connected layers and try to see whether this difference can be reduced or not. So this way you can tune your own custom design model to whatever the performance level you wanted to achieve. You can try this. So you can try all the options I have mentioned. So here I have commented here, right? No, this one you try to uncomment and see the performance. And secondly, you try to reduce the filters instead of 16 filters, make it like maybe 10 filters or 8 filters and see the performance. And change this SGD to Adam and again see the performance. All these variations you can play around. So this is the way you have to build your own custom data set, how you have to prepare your data set and the labeling and how we shuffle the records and how do we split the record for the training and validation records. And many times, okay, unless otherwise you don't work on some special imaging domain. Say, for example, you are building an application like some different plant species. Okay, some food processing in agricultural application. I wanted to build a deep learning model. Some, say, for example, some medicinal plants. Because not everybody is a domain expert about identifying some herbal plants. No, hardly we know some 3 herbal plants. We know tulsi. Okay, tulsi is from by looking at the leaf of the tulsi, you know which is tulsi. Okay, maybe a few herbal plants we know, hardly one or two herbal plants we know. But imagine that you wanted to build some deep learning architecture by looking at the photograph. Okay, some domain experts, some hundreds of different herbal plants you wanted to differentiate it. So for each classes, you need to have a photograph of different leaves patterns you have to collect. You can train a deep learning architecture to classify which species it is. You can build an application for this. One way is you can build an application right from the scratch. The second way is you can use a pre-trained model. Pre-trained model has trained using some popular data set like ImageNet data set, visual computing data set, VCC data set, like some standard data sets are available. There are around 50,000 classes are there. the living things, non-living things, whatever we see in the day-to-day life in and around us, all wild animals, all domestic animals, all non-living things like commonly found the car, desktop, a laptop, pen, table, chair, house, horse, rat, rabbit, like 50,000 commonly available objects. Some models, popular models have been already trained. But maybe your case study is identifying different herbal plants. Okay. Maybe your ImageNet data set may not have all these herbal plants, but it has got some type of plant species. Okay. It might have some common plant. Okay. Maybe this is being identified as something like a plant or tree. It may classify. Not a specific type of plant, may not be. Okay. So this is the problem statement. The problem statement is already some pre-trained model know what is plant. Okay, but may not say that what is a specific type of plant, whether it's a herbal. Herbal means what is a particular type of a herbal plant and all. I will show you some of the popular pre-trained architecture, how it looks. In Google, if you search for the architecture I'm going to show you here is there are two pre-trained model I'm going to use. One is the VGG16 for this, once again for the image classification task. Another example for the object detection task. Object detection task also extension of the same thing, but only difference is in single frame we are going to label multiple objects. That's an extension of this idea. I'm going to tell you how this idea can be extended for the object detection task. So for that, I'm going to use another pre-trained model called MobileNet, which is very compact. It occupies less memory. Comparatively, it occupies less memory. This is VGG16 architecture. If you go to image page of this, your VGG16 architecture uses several layers. You can see so look at the architecture of VGG16. It has used so many convolution layer. Can you notice? That is a feature to the feature it is applying. First derivative, second derivative, followed by a pooling layer. So there is no specific design constraint. Like there is no hard and fast rule saying that after convolution layer you should apply a max pool. You can also apply convolution result. Once again, you can apply the second derivative and then you can apply max pool. It's a complete our design choice. Here you can see there are two convolution layer followed by one max pool. Again, there are two convolution layer followed by a max pool. There are three convolution layer followed by one max pool. Likewise, so many layers. This VGG16 has been trained to classify 50,000 classes available in the real world and able to give the accuracy close to 98%, 97 to 98% accuracy. So already these popular architectures are already proven architecture. Okay. So what is the idea of using the pre-trained model is you're going to take some proven architecture and you're going to little bit fine tune the architecture. What is meant by fine tuning the architecture is, say for example, I don't want to rebuild the whole architecture from the scratch. Say for example, I wanted to utilize whatever the weights, these features, these convolution layer, whatever the weights it's extracting, I don't want to disturb those weights. Okay, I'm going to freeze this. Now I can allow only these three layers. I'm going to allow to train my pool of data, your pool of data set, and these portions again you can design according to your design considerations. because here you don't want to classify 50,000, right? Here I want to classify only, say for example, in the case study, I'm going to show you 12 different species. 12 species I wanted to classify. So you can decide till what layer you wanted to freeze, which layer you are going to allow to the learn. You are going to expose your own data set. This is called transfer learning. Again, it is your convenience. Okay, till which layer you wanted to freeze. You wanted to only the last two layer you wanted to allow for the learning, or the last three layers you want to allow for the learning, or only one layer you wanted to allow for the learning, till the last but one you wanted to freeze. The idea here is your initial few convolution layer will have the course details or popular objects, including the tree, including the plant, isn't it? It will have the course structure, because a tree means the trunk of the tree should be like this, the branch should be like this, the course edges. But the delicate features, who's capturing the delicate features? The tail end of your model. These guys will have a delicate, now what will be the shape of the leaf, how the veins will be running inside the leaf. So the finer details. Now I wanted to relearn the finer details according to my own data set. Let me not disturb the course details. So I wanted to maintain the course detail as same as my popular VGG model, how it learns the course detail of multiple objects. I don't want to disturb. Along with that, I am allowing my model to learn my own 12 species to update. So along with this knowledge, my model is going to update with this knowledge, additional knowledge. Thereby, you can customize your already pre-trained model. You can customize according to your own application. Thereby, you can save plenty of time building your model from the scratch. So this kind of approach, what kind of application you can follow this? If at all your own database, okay, our own database, should have some similarity with the popular data set like a ImageNet data set. See, if you are working on the plant species example, yes, of course, ImageNet, we have some commonly available plants are being classified. Okay, like a sunflower plant or hibiscus, these kinds of plants, some data are there, but not particularly on a particular medicinal value plant and all, not specifically there. That is why you wanted to expose your own custom data set to the pre-trained model, and you are aligning the weights according to your own custom data set. But some applications, you have a database which is not at all used in the ImageNet, not at all used. It's a very special cases, mainly or medical example and all. Say medical, there is an ImageNet, there is no standard medical images were used. Okay, there were no medical images like MRI or ultrasound on any specific case. Say you are working on medical images on an Alzheimer's disease or a Parkinson's disease or a particular type of a lung cancer or a particular type of abdominal cancer. So the popular ImageNet dataset or Vision Studio datasets, vision computing datasets are not having that standard images. So for that kind of application, I cannot apply pre-trained model. You have to build the model from the scratch, like the way how we build the model for the malarial cell dataset. We have to build the model from the scratch. But for the common objects, we can very well use the pre-trained model. So I have shared the link for this to download this data set. This is one of the popular data sets shared by Signal Processing Group, University of Southern Denmark. So they have shared 12 special plant species. I'll show you the image folder. Once you download the image folder, it will be available like this. So I have you have got the link now during the instruction. When you download that link shared with you, there are around 12 different folders. You can see black grass, charlock, clavers, common chickweed, common wheat, fat hen, low silky bent, maize, mayweed, shepherd purse, small flowered grain, and sugar beet. There are 12 classes. You just open a particular folder and see. You can see the shape of the leaves. Okay, something oval, this kind of pattern. Okay, some other plant species, if you see like a charlock, you can see the pattern, little heart shape, slightly different shape. And some other species, if you see like I take common wheat. Again, the shapes are different. Okay, it looks like a grass, but a little broader leaf. But grasses will be very thin leaf, you can see, because we have a separate folder for black grass. It will be more thinner leaf. You could see it's a more thinner leaf. But however, there is one more class which is almost similar to the black grass. That is called low silky bent. Strictly speaking, this low silky bent and the black grass should be kept as common class. Okay, both guys should be in the same class. But however, I wanted to show you, okay, if the patterns are very similar, closer, how your model is going to struggle. I wanted to show that particular process. Purposefully, I kept this as a two separate class. Black grass and the low silky bent are almost same. But however, I kept this in a two different labels. But other species are, we have quite a difference in the shape and structure. Small flowered cranesbill, you can see the pattern of the leaf. Visually, we can notice a difference, good difference. Okay, you can see patterns are different. Likewise, totally I have taken 12 unique classes. I'm sharing the notebook in the code share. You can download this file and follow the steps along with me. Okay, how do we prepare our architecture using the pre-trained model? Just a moment, please. I'm sharing the file. So don't run the full notebook. I'll tell you step by step. Just follow the instruction. Suppose, see, when you download from the link, it has already been shared with you. Not this link I'm talking about, your data files. All the data files links have been just before the workshop itself shared with you, right? Those link, when you download it, it will be downloaded as a zip file. Zip file. One way is you can unzip in Python environment. You can extract all the files. Another way is you can unzip it outside the Python. Regular way, how do you right click and you can unzip, no? You can unzip it and keep it as an unzipped folder. That unzipped folder, you have to upload it. Okay. So don't upload as a zipped version. Suppose if you are uploading as a zipped version, you should run these two cells. Okay. I have already unzipped this, so I'm not running these two cells. You have to tell which location you have to, your zip file is available. I have to tell that content drive, my drive, dl test.zip. Similarly, train.zip. These two folders, I'm going to unzip it. Okay, in Python environment, because already being unzipped for me. So I'm telling my current working directory. I'm referring my current working directory. Change directory is content drive, my drive, dl train. So my current working directory is referring to train folder, right? Okay. Now I initialize my X train, Y train as an empty list. Now when I say os.list directory in the label names, okay, it is going to get all the label names of the 12 classes. Clavers, Charlock, Common Wheat, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 classes. Okay. Now I can say os.path is directory black grass is there. I can ask the question. It will say yes. There is a black grass directory in my current working directory. So any folder name, if you ask, it will return true. Suppose when I ask for a different, which is not part of this, when I ask for, is there any 12C folder is there? It will say false. There's no such folder is there, isn't it? When I ask for clavers, that folder is there. It will return true. See what we are doing here. We are reading all the images in the train folder and we are resizing it to standard size 128 by 128. And we are appending that in X train and Y train. So the resized image, all the resized image, it will take a few seconds. Now it is, can you see it is working for the clavers folder? All the images, it is resizing to 128 by 128. It is appending in the X train and the corresponding, the label name is being appended in the Y train when you are running this loop. Second folder it is working on. Now it is working on the common wheat. Now black grass. Look at the runtime. My runtime is enabled GPU. That's why it's faster. If you're running on the CPU, it may be a bit slower for you. So it is working on fifth folder, low silky bent now. Once this for loop is completed, I'm processing all the training images and the processed image is being stored in X train and the corresponding label is being stored in Y train. Okay. Put together all the classes, you can see there are 4,750 images are there. Put together all 12 classes, 4,750. Length of the X train also you can see 4,750 images. Okay, if you check what is the size of the first image in X train, you put square bracket 0 dot shape, it is going to show you 128 by 128 by 3. Okay, because we have reshaped all the images to standard dimension 128 by 128. That means we are going to use the color images itself directly. Okay, because to identify the plant, because the color feature also plays an important role. The green color component plays an important role. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, this is the 12th class it is working on. So all 12 classes it's prepared. And see, when I ask what is the length of X train, 4750. What is the length of the corresponding weight line? It gives 4750, right? And any specific location, if you ask the size, it will say 128 by 128 by 3. And here I'm going to do the dummy encoding, labels, encoded labels. So there are two ways you can create a label. One package is NP utils we have used in the last two exercises, but parallelly you can also use another package which come from a NumPy package called as a dummies, pd.getDummies. From the pandas package I'm using this pd.getDummies. So when you check your y train now, y train square bracket 0, the first y train. Sorry. So it will be created like this. So the first y train record is the clavers. Okay, for the cleaver class it is 1. Remaining all the classes probability is 0. The few records are cleavers. Maybe I can show you like tail of this. The last few records. See the last few or sugar beet, right? Okay, because so far we have not shuffled it. It is in the order. So the first one starting with the cleavers. Okay, first one starting with the cleavers and the last one ends with sugar beet. So if you see the head and tail, because we have used this time a different package pandas, that is why your one hot encoded label is represented like a data frame. Okay, so it doesn't matter. Either package you can use it. So the last 5 records, when I display my labels, you can see sugar beet is encoded as 100% probability. The remaining classes are 0% probability guess. So your X train, I have typecast this in the form of a NumPy array format. Because initially we have created in the form of a list format. Here it is in the list format. From the list format, I converting to the array format here. So after converting to the array format, you can see X times shape 4750 image. Each image size is 128, 128 by 3. Similarly, the labels 4750 cross 12, right? 12 one hot encoded. So since you converted to array format, now you can print a square bracket 0 and you can see. Earlier, when I was trying to print square bracket 0, it was not showing because it is the form of a data frame structure. Now I converted to the array structure, you can put a square bracket 0 and you can see. Maybe randomly I check like 1200 index record belong to this class. Okay, 1800th record belong to this class. And 2800th record belong to this class. So randomly you can check. And also randomly you can check the images cv2.im show in X train. Maybe 145th index, I wanted to see what is an image. This is this pieces. Okay. 1200th index, I wanted to see what is an image. Silky bend, low silky bend it is. Then 1900 index, what is an image? I think this looks like this. I think this is common wheat. So randomly you can check a few images just to make sure that all the images are in properly processed and placed it. What is the next step? So far it is in the order, right? Now I'm going to shuffle it and I'm going to split it. So using a train test split, I split this record, 3800 record for the training, 950 records, I'm going to use it for the validation. So I scale the record, scale by 255, max scaling. So we have the data ready to feed to our model. 3800, 128, 128 by 3, 950, 128, 128 by 3. So here I can use a pre-trained model from the applications. From TensorFlow.keras import applications, I'm loading my VGG16. You can see this is the main part of this code. So what is the syntax? Application.vgg16. I'm saying that include the top false. That means include top false means what is the meaning is your fully connected layer. Okay, don't include the weights, because I'm going to say that the fully connected layer, it is our design. Okay, it is a custom design. We are going to design. Till all the convolution layer, it is going to load all the layers. I'm telling the model to load all the weights. And here also I'm going to design in such a way that till layer number 10 or till layer number 12, I wanted to freeze. The last two layers I wanted to allow for the learning. That I can define later on. For while loading the model, what I'm saying that include the top false means don't include the weight of the fully connected layer. That is the meaning. And also I have to specify what is the input shape we are going to use, 128 by 128 by 3. Okay. So now I need to run this cell, loading all the libraries. Okay. We are defining the model here, application.vgg16. Again, this VGG16 architecture has been trained for some of the popular data sets, like ImageNet is one popular data set. Visual computing data set is again another popular data set. Some 3 or 4 database has been trained. Out of all the databases, this ImageNet database handles so many classes. That is why ImageNet is highly preferred. You can also try with other databases also. If you go to the documentation page of VGG16, there you can see which are all the image data standard data set this VGG16 has been trained. You can see those names. But which is highly preferred is ImageNet is highly preferred because it has 50,000 classes have been trained on it. So here we are loading the pre-trained model without the top layer. See, our pre-trained model is loaded. Now here, this is the customization. Here you can define, you can play around with the numbers. Till, okay, you can see model.layers. If you print, it will show all the layers. Your complete VGG16 architecture. When you say model.r, whatever you have seen in the block diagram, because we have specified include top false, it will not show the fully connected layer. Okay, it will not show the dense layer. It will show only the convolution layer. You can see convolution layer followed by max pool. Convolution, max pool. Hope you remember the block diagram, same as the block diagram. Followed by 3 convolution, followed by max pool. Again 3 convolution, followed by max pool. Finally 2 convolution, followed by max pool. Here you can design till how many layers you don't want to train. You wanted to freeze, that you can specify. For layer in model.layers :10, I'm saying that false. Okay, first 10 layers I wanted to freeze. 1, 2, 3, 4, 5. It will consider the first 10 layers or 12 layers. You can play around with this. So which score gives the better results? Accordingly, you can play around with this. Again, there is no fast and strict and fast rule saying that only these many layers you should freeze, only these many layers you should. According to your pool of data set, if you feel that okay, these data sets already ImageNet data already have several images, why don't I train only the last couple of convolution layer alone? Let me freeze 15 layers, let me freeze. That way you can decide. Or if you feel that your data set is of very less resemblance to ImageNet classes, maybe you have to freeze very less number of layers. You have to unfreeze more layers. You have to reduce this number. Okay, but here in this exercise, I'm freezing first 10 layers. I'm freezing. I'm saying that don't train. So there onwards, this is our custom layers. From there onwards, automatically the remaining layers model will learn. But you have to design your fully connected layers. No, So from here onwards, our fully connected layer design goes on. Actually, this is a fully connected. So model.output. So model.out means your trained, pre-trained model. From here, you take the output, right? From here, you are taking the output. That output is being flattened. We are feeding that as an input to the dense layer. Okay. So from this, whatever the pre-trained architecture, we have frozen till 10 layer, and the remaining layer alone, we are allowed to the learning process. Model will learn, update the weights of this remaining layer. And after updating, what I do, I tap the output and I flatten it, give as an input to my first hidden layer with 1024 neurons. I introduce a dropout layer, I told you, right, for regularization term. Practically 20 to 30% is highly recommended, but however, I have used here 50% is quite slightly high number. But however, we can tune this later on. Then followed by a dense layer again. If at all, if you wanted to introduce one more dropout layer here, means over regularization leads to underfit. Okay, but between my first hidden layer and second hidden layer, I say 50% of the neurons, I make it as not a trainable fashion. That means I'm allowing 50% of the neurons between these two layers. That means how many weights will be there between these two hidden layers? 1024 into 64. 1024 into 64, that many weights. 1024 into 64, we get 65,536. Out of which 50% I say dropout, nearly half of this. Okay, half of this. That means I'm allowing only 32,768 weights to learn. So that is the meaning of this dropout layer. If you feel that this is too much, maybe you can control this to maximum 30%. So only first you have to see whether your model overfits, then only should introduce. Before seeing that your model is not overfitting, this is not needed. Okay, not mandatory. Since already I see the result, that is why I have been introduced this. But the first time when you run, you don't include this line. So another hidden layer with 64 neurons. So totally we have used 3 hidden layer, and finally the output layer with the 12 neurons. So this is, since it is a custom design, okay, I have to wrap up everything in one single module called model. While importing, I have imported something called model, keras.models, because it is being a custom design, it's not a regular design. So I have to put everything in model. What is input, what is output, that you have to define. So your pre-trained model dot input will be go as an input, because as per the definition, what your model input is, whatever is being defined, your input shape, it is going to accept this 128 by 128 by 3, that design. And whatever this predictions, this final output, that will go as an output. So that I'm just tying both the ends, starting and ending of your architecture. I'm just wrapping up. It's just encapsulating the starting and beginning and end of your design. You're encapsulating in one single architecture like model. And then finally you compile. This portion is same as your earlier categorical cross entropy, because it's a 12 class. Optimizer is again SGD or Adam. So this is the design. So we go with this design, and in the previous exercise, one way to save your best model. Okay, that is one way. The another version, which is a very easier version, is you can make use of the built-in package like model checkpoint, early stopping. So this is another way to store your best. There you can drastically reduce the number of lines. All the authentication, credential, all these things you can ignore. Directly you can use this model checkpoint. You can give a name. Okay, you can give a VGG16. So during which iteration you got the better accuracy, that particular iteration result will be directly saved by this model checkpoint. So that can be controlled by early stopping. So it will keep on monitoring the accuracy and a particular iteration. So I give a patient score of 5. At least wait for the first 5 iterations. Don't take the best score. You take the best score after the 5th iteration. Likewise, you are telling that. So beyond 5th iteration, which was the best score your model iteration has reached, that score weight value will be treated as the best result, and it is being saved as a VGG16 best5.h5. Here you can give any name of your choice. So here I'm training for the 20 epochs. So it will run all the 20 epochs, but out of all the 20 epochs, which epoch gives the best accuracy result, that result will be saved as the best result. So this is being executed. Okay, now I come to this cell. I don't want to rerun this. I don't want to override this .h5 file. This is already created in DLVGG16. I'll show you that. In DL, we have got what name we have saved. It is VGG16 best, right? But in your system, you can run, because the first time you're creating, you can see VGG16 best 5.h5. So I skip the step. Already my best result is stored in VGG16 best 5.h5. Okay. So I directly load that trained model here. We are loading that model. Okay, you can see that model summary. This is our last few layers. This is our custom architecture. Hope you remember. After flattening, this is 8192 features are there. From here onwards, first hidden layer, followed by a dropout, second hidden layer, third hidden layer, the output layer with the 12 neurons. So randomly, you can check any one image, how your model is classified. So in the validation folder, 0th index, okay, 0th index, this is the plant species. Suppose I wanted to verify that. So trained model.predict xval. For one record, it is going to give one prediction score, but I'm passing the entire value xval. So remember, what is the shape of the entire xval? You can see totally we are going to validate 950 images, not just one image. So when I say model.predict xval, it is going to do the prediction for all 950 images. And if you wanted to see what is the prediction for the first case, this is the first case. No, this is the first case. What species is this? If you wanted to check, you can ask the PRED score. I think this is the highest probability, right? 0, 1, 2, 3, 4, 5, 6, 7, 8. Arg max, it is going to return 8. And if you wanted to know the class name of the 8th index, the species belongs to maize species. It belongs to maize species. Some other location, if you wanted to cross check, maybe the 10th index, I wanted to check, because they are shuffled actually. This is a different species, right? This is a 10th different species. So I wanted to know at the 10th index, what is the prediction? Who is the highest probability? The highest probability is, I think, 0.66% probability. Yeah, sorry. Yeah, that is 0.66. So the index number 8. 0, 1, 2, 3, 4, 5, 6. Sorry, I didn't run this for 10th index. It is 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11th index. 0.66% probability. If you wanted to know what is the class name of this 11th index, sugar beet. Likewise, one by one you can verify, or you can see the validation report. You can see the validation report of this, the entire prediction. Because you have to do the argmax for the entire record, right? You have to prepare whatever it is going to predict in the form of a probability score, one hot encoded value. When I have to apply argmax to each and every predictions, I have to convert to label, class label. So that one I'm doing it here. So all your predictions are stored in which variable? Ypred, right? ypred in the form of 12 by 1 vector. This 12 by 1 vector, I have to convert it to integer type. So how do I do this? I have to run this loop. Y label, okay, Y label, for loop I'm running here up to the entire range of ypred. I run this loop to get all the Y label. Similarly, the actual labels also in one hot encoded version, I'm converting to the integer labels, Y actual. Now I can print the classification report. You see the overall performance is good, not bad. 94. I told you the least score we have got. Okay. So almost all the classes are 90 and above. Okay. The least score is what we got for the class label 11, 79%. And the second least is 87%. Also, you can display the confusion matrix for this. So using the pre-trained model, we have got a very decent score. Still, you can fine tune this. One way to improvise the result, as I told you, silky, bent, and the grass, you can put it in a single class, and still you can improvise the performance. So this is the way you can use the pre-trained model. Any question on using the pre-trained model? Are you clear with the approach of using the pre-trained model, how you can use the pre-trained model for our own custom data set? Any question?